So this video is about molar mass and formula mass. So we've already learned a little bit about the mole, and so let's look at this compound right here. That's right here. There we go. So this is a molecular compound. It's a molecule of carbon and two oxygen atoms. That's what makes up that molecule. So if we wanted to, we could draw a little sketch. So here's a carbon atom, and here's an oxygen atom next to it, and here's another oxygen atom over here. And so these are all bonded together. So that makes one of these carbon dioxide molecules. So the idea behind molar mass and formula mass is we want to figure out, okay, if you had a mole of these guys, and remember a mole is just a big number, how much would that weigh if you put it on the scale? That's what we mean by molar mass. Molar mass is just the mass of 1 mole of that stuff. So let's figure out how we would calculate that. So what we know about molar mass is that the mass in grams of 1 mole, we can get that off the periodic table. But what if we have a molecule? Well, if you have a molecule like CO2, all you have to do is add the masses up off the periodic table. So, for example, carbon, we know has a mass of 12.01 AMU, right? So that means if we have a mole of carbon atoms, on average, it will weigh 12.01 grams. Similarly, if we have oxygen, oxygen weighs 16 grams, or 16 AMU, rather. That's supposed to be a dot. So 16 atomic mass units. So what's a CO2 going to weigh? Well, the mass of that plus the mass of 2 of these oxygen atoms. So the mass of 1 carbon atom plus the mass of 2 oxygen atoms will give you the total mass of one of these molecules in AMU. And we can get the molar mass the same way. So the molar mass of CO2 we can get just by adding up the molar masses of the atoms that make it up. So 12.01, and we're going to call that grams per mole. And so this little unit label right here just tells us that there are this many grams in every 1 mole. So we're going to add that to, now we've got 2 oxygen atoms, so we're going to take 2 and we're going to multiply that by 16 grams per mole. All right, so where do we get the 12 and the 16? Right off the periodic table. And so you add all that up, and you'll get the total mass of CO2. So 2 times 16, that's going to be, you can do that in your head, 32, right? Plus another 12, 44, right? So we're going to say 44 right here, 44, roughly 0 grams per mole. All right, so that would be the molar mass of carbon dioxide. Now we use this other term, formula mass, when we're talking about things, substances that do not form molecules. So these would be like ionic compounds. Remember, ionic compounds don't form molecules. They form an extended crystal lattice. So let's say we had sodium chloride here, NaCl. So NaCl, right, remember what we've got is a crystal lattice made up of these positively charged cations, the sodium cations, and the negatively charged anions. And they stack up like Lego bricks to make a big orderly arrangement. We call that a crystal lattice. Okay, so there's an example of NaCl, and I would keep on building this up, on and on and on, stacking in front and back, top, bottom, left, right, all that kind of stuff. But this part of it right here, so I'm just going to circle that, that's what we call a formula unit. So this formula right here tells you that for every 1 sodium cation, you have 1 chloride anion. So that has to be the case to have charge balance. And so this thing is the smallest repeating bit of sodium chloride, and we call that the formula unit. So formula mass is just the mass of that 1 formula unit, and we would calculate it the same way. So for sodium chloride, we would just look up the mass of sodium off the periodic table, and for round numbers, it's about 23, so 22.9897 blah blah blah. So we're just going to write that as 23. So 23 grams per mole for sodium. And we're trying to calculate the formula mass, also sometimes called the formula weight. By the way, you'll sometimes hear these masses called, instead of molar mass, you'll hear it called formula mass or molar molecular weight. So all these terms are more or less synonymous, but molar is letting us think that we're talking about moles here. So formula mass, the mass of 1 formula unit, right? So this thing right here is called a formula unit. right? So we're going to then add that to the mass of chlorine. What's the mass of chlorine off the periodic table? 35, whoa, 0.45. Oops, 45. Right, grams per mole. And so you just add those up, and you get the total molar mass of one formula unit of NaCl. All right, so let's scroll down here and we'll show you how you can use these numbers a little bit. So one thing that's very important is to be able to go from mass in grams back and forth between moles of a substance, and then we might actually want to know the actual number. So how many actual things do you have? How many actual molecules? How many actual atoms? And the way to go back and forth between grams and moles is by using this number that we've just talked about, the molar mass. The way to go back and forth between moles and number is to use Avogadro's number. So sometimes that's abbreviated capital N with a little capital A as a subscript. So N sub A, so for Avogadro's number. Right? And so that's that 6.022 times 10 to the 23rd power number. So we can use that to go back and forth between these. So if we know the grams, we can find the moles. If we know the moles, then we can use Avogadro's number to find how many actual things you have. And we can go back and forth between these any way we want. So let's do an example. Let's say, for example, we have 18 grams of carbon dioxide. So 18 grams of carbon dioxide. And we would like to know, well, how many moles of carbon dioxide molecules is that? Well, we can use molar mass exactly like a conversion factor. So I've got 18 grams of CO2, and I want to get rid of that grams of CO2 unit. So I'm going to need a conversion factor here, and so I write it like this in parentheses. Now sometimes you might have learned to draw a straight line and put little slashes in it. That's just fine. So this is the way I do it. So here we have in parentheses. And what unit do we want to get rid of? Well, grams of CO2. So that goes in the denominator, right? Because we can cancel it out that way. So grams of CO2 up here gets divided by grams of CO2 here, and they're going to cancel like that. What unit do I want up here? Well, I want to know moles of CO2. So I'm going to write MOL CO2. Isn't that a great abbreviation for mole? Oh, we're going to leave off that E because, boy, that saves writing. That's a lot of writing, I guess. I don't know. Anyway, so now what we need to do is go back up to where we did our calculation. So remember that we calculated our number of moles. There it is up here. It's 44 grams per mole. So next to the gram unit, I have the number 44. Next to the mole unit, I have a 1. So that's what I'm going to recopy here, a 1 and a 44 down here. So 44.0. All right, so what does this tell us to do? It says take 18 and divide it by 44. That's how we're going to figure out what unit is left, the moles of CO2. So we'll go and do that. Let me bring my calculator up over here. Yeah, so here's your calculator. So we want to take 18 and we want to divide that by 44. And what does that equal? Oh, too many times. Let's try that again. 18 divided by 44 is equal to 0.409 or 0.41 in round numbers. So we're going to say 0.41 moles of CO2. Let's check and make sure that this makes sense. Let's see, we've got to have a whole 44 grams to have 1 mole of CO2. We only have 18, and 18 is less than 44. In fact, it's even less than half. So we would expect to have something less than half a mole, and that's what we calculated. There we go. So now we figured out how many moles of CO2 we have. Now let's take this calculation one step further and ask this question. So if we know how many CO2 moles we have, how many actual oxygen atoms do we have in this sample? So we want to know how many actual oxygen atoms. So we can do that kind of conversion right here using some conversion factors, all right, and Avogadro's number. So 0.41 moles of CO2, that's what we just calculated. All right, so from the formula, what do we know? Well, we want to get rid of this moles of CO2 because we're trying to figure out number of oxygen atoms. So as a step along the way, we're going to go from oxygen atom, we're going to go from moles to, we're going to go from moles, here we go, of CO2 to moles of atoms, right? So we want to get moles of oxygen atoms right here. We want to get rid of that moles of CO2 unit right there. So I put that in the denominator so it will cancel out. So from the formula, what do we know? We know right here that we've got 2 oxygen atoms for every 1 whole carbon dioxide molecule, right? And remember my sketch from the beginning, if we go back up here? Yeah, so we've got 1, 2 oxygen atoms for every one of these. So if we happen to have a dozen of these guys, we're going to have 2 dozen oxygens for every 1 dozen of these molecules. If we have a mole, we're going to have 2 moles of oxygen atoms for every 1 mole of these molecules. So I'm going to use that as a little conversion factor. So I'm going to scroll back down here. So here we go. 2 moles of oxygen atoms for every 1 mole of carbon dioxide. So I'm going to take this 0.41 and multiply by 2. Why? Because I have 2 oxygen atoms in every one of these. Now I need one more conversion factor because I want to get actual number of atoms. So here's my next conversion factor. And actual number of atoms, well, that's Avogadro's number right here, this conversion factor. So I know that from Avogadro's number that there's 6.02 times 10 to the 23rd atoms in every 1 mole. So that's another way of thinking about Avogadro's number. It tells us the number per mole. And so now moles of oxygen will cancel out. Moles of CO2 is canceled out. And so when I do this calculation, I will have my final answer. Let me scroll down, and we'll scroll over here, give myself some more space. And we should bring out the calculator again and see if we can do this calculation. All right, so let's clear that. So it says I need to take my 0.41, and I'm going to multiply that by 2, so times 2, that equals that number. And now I'm going to multiply it times 6.02, times 10 to the 23rd. Now, if you don't know about this, most calculators have an EXP key, or on the TI calculators, it's usually an EE key. And if you type that, it's going to bring up this little symbol. So 6.02E. What does that E mean? It means times 10 to the whatever. So I'm going to type in 23rd here. So now that number is 6.02 times 10 to the 23rd power. Okay, so I'm going to set equals. And there we go. So now we've got a really, really big number. So this button on this calculator will bring that into scientific notation. So there we go. It's a number that's about 4.9. So we're just going to, we're going to call it 4.9 times 10 to the 23rd. So there we go. 4.9 times 10 to the 23rd oxygen atoms. All right, so when we take 0.41 and we multiply it by 2, we still don't get all the way up to 1 mole of oxygen atoms. So we don't have a full 6.02 times 10 to the 23rd of them. We have something less, right? So that makes sense. All right, so that's how you go from grams to moles to numbers of atoms. And notice we use this little intermediate step when we had to calculate a part of a larger whole. We just used the 2 atoms to 1 whole ratio there. So there's that 2-to-1 ratio. So a lot of these chemistry problems are about just using these ratios. And if you use your factor label method to cancel out your units, including the chemical compound, that will really help you make sure you get the right answer in the end. And tell you if you're leaving something out, like if you forgot to do this 2-to-1 conversion.